Hello teachers! Welcome back. This is section 3.4, and in section 3.4 we're going to discuss multiplication of whole numbers. So we've thoroughly discussed addition of whole numbers, then subtraction of whole numbers. Now we want to move on to multiplication. At the end of this video lecture, at least by the end of the homework, we hope that you can discuss multiplication through various models. We want to talk about properties of multiplication and how to use them to develop computational strategies. We want to talk about multiplication algorithms, including the standard algorithm and how to use them to solve problems. We're going to do multiplication with number bases other than 10. I know that's your favorite. And then we want to talk about mental multiplication skills and estimation techniques. Multiplication of whole numbers can be modeled in several different ways. As you can imagine, the repeated addition model is a great way to think about multiplication, because multiplication can be thought of as repeatedly adding the multiplicand multiplier times. So for instance, maybe words here that you don't recognize. So for instance, if you multiply 2 times 3, 2 is the multiplicand and 3 is the multiplier. So that's the same thing as adding 3 2 times. That's 3 plus 3, of course, which is 6. And we'll do that in more detail in a few minutes too. But another model is an array and area model. They are two different models, but they really express the same idea. Multiplication can be visualized by constructing an array of crossed sticks or a grid and counting intersection points, or just grid components when you're talking about area. Then there's the Cartesian-Product Model, which is multiplication can be thought of in terms of a Cartesian product. You remember a Cartesian product is a set of ordered pairs. And we will talk about all of those models in detail. The first one being the repeated addition model. So if we have 4 groups of 3 brushes, we can use addition to put the groups together. When we put equal size groups together, we can use multiplication. We can think of this as combining 4 sets of 3 objects into a single set. So we have, notice, 4 different sets, 4 sets of 3, and of course we know 3 plus 3 is 6, plus 3 is 9, plus 3 more is 12. So that is the repeated addition model. That's a great way to introduce multiplication. And here is a visual of the repeated addition model, right? So we have 5 times 4, this time is what we're trying to express. So that would be 5 groups of 4. You'll see that in the blocks here. So at the bottom row, we have 5, again, groups of 4. Or that's the same as 2 groups of 10, which is 5 times 4. And we all know that's 20. With the number line, you'll notice that it's like repeated, it is repeated addition. So 4 plus 4 plus 4 plus 4, because remember, addition on the number line, you take your first add-in starting at 0 and then stack the next one at the end with no spaces in between. So 4 plus 4 gives us 8, and we continue on until we do 5 of those to get 20. And before we continue any further with our models, let's talk about a definition of multiplication of whole numbers. And this is the repeated addition model. So for any whole numbers a and natural number n, then we can multiply n times a, where n times a is a repeated n times and added. That is the repeated addition model. Now, what about the rectangular array model? So if you're trying to express 4 times 5, notice what we have here. The 5 is represented horizontally. So if you'll see, you've got across this way 1, 2, 3, 4, 5. And then if you want to multiply that by 5, you do that 4 times. So again, we have 4 rows of 5. And to get to 20, you'll notice our intersections are made with dots, and if we count those dots, that'll give us 20. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Or, to reinforce the fact that this is 5s, 5, 10, 15, 20. You could also use the area model. And notice again, we have our first area here of 5 units, and we have 4 rows of 5 units, which gives us 20 blocks if we were to count all of those. Very similar models. One, again, is just talking about the intersections. That's the rectangular array. And the area model is considering how much space these take up. In other words, you've got 20 squares here. Then you have the Cartesian product model. So suppose you plan to take 2 web-based courses at your local college. You can take one of the following. You can take world history or ancient history. For your second course, you can take one of the following: Latin, French, or German. Now, to show the number of different schedules you could have, you can use a tree diagram. As you could imagine, if we started the tree, well, better yet, let's don't. But you know what we mean by tree diagram. So you could start off by saying you could take world history. I'm just going to use WH, or you could take ancient history. Now, if you take world history, then to take your next class, you could take Latin, French, or German. Or if you took ancient history, you could take Latin, French, or German. And I said I wasn't going to do it, and I did it anyway. Although I do think I have a typed up version that looks a little bit better. Hold that thought. The ways of designing your schedule are a result of selecting a history course from world history or ancient history, and a foreign language course from Latin, French, or German. I think we had established that, right? And then here is what I drew. So your schedule, you can go world history or ancient history. And then off the world history choice, you have Latin, German, or French. And off of ancient history, you also have Latin, German, or French. And then there would be your schedule, world history and Latin, by following the branches, or world history and German. Or, again, you follow the branch, world history or French. Or you could go ancient history Latin, ancient history German, or ancient history French. Right? How many outcomes do we have? Looks like 6 to me. Now, if you'll recall, the way to calculate this is the fundamental counting principle, right? So we had 2 choices for our history class, 2 times 3 choices for our language, and that's the 6 choices we expected to see. And here you go. The fundamental counting principle tells us that the number of ordered pairs, H cross L, is 2 times 3, which is 6. So you could also define definition of multiplication of whole numbers using the Cartesian product model. So if we have finite sets, A and B, and if you'll notice, the number in A is A. Okay, now the way we really read that is the cardinality of set A has A items in it, and the cardinality for set B has B items. And the fundamental counting principle tells us if you can do something A ways and you can do something else B ways, then you multiply those together to get A times B, which is also the cardinality of A cross B. So it says in this alternate definition, sets A and B do not have to be disjoint. The expression A times B, or simply AB, is the product of A and B, and A and B are what we call factors, because those values multiplied to give us our result, which is the product. Well, let's talk about properties of whole numbers. If we introduce a new idea, which is multiplication in this case, we want to know what properties we have available to us. And the closure property of multiplication of whole numbers does apply. If you multiply whole numbers together, your answer is a whole number. For fact, if you multiply any 2 whole numbers together, your answer is still a whole number. Unlike subtraction, remember, if you subtract 5 minus 8. Your answer, -3, is an integer, but it's not a whole number. So subtraction is not closed in the whole numbers, but multiplication is. Hey, we also have a commutative property. And the commutative property of multiplication says we can multiply in different orders. So A times B turns out is exactly the same thing as B times A. We'll look at a visual of that in just a minute. We also have the associative property of whole numbers available to us. Remember, associative, think root word associate. In this first line on the left of our equation, we've associated A and B together, and then we take that answer and times C. Well, it's perfectly okay to associate B times C together, multiply that, and then take that result times A. You get the same answer. But notice overall, the order from left to right is the same. We didn't commute. We didn't move anything around. We just associated differently. And then we have the identity property of multiplication. Okay? Now, if you'll think back, subtraction doesn't have an identity property either because it doesn't have a commutative property. Identity means that you can do there's a number that you can do your operation with, and you get the same answer that you started with, okay? And you have to be able to do it commutatively. So the identity, the multiplicative identity, is the number 1. We know that A times 1 is the same thing as 1 times A because we have the commutative property, and both of those equal A, the value you started with. So anytime you want to not change the value of a number, you can multiply it by 1 and you will get the same result. Now we have a new property, the multiplication property of 0. What happens when we multiply by 0? We get 0 as an answer. So that is something that we need to keep in mind. Whenever you multiply by 0, you get 0 as an answer. Now all these properties we've just discussed, we can depict this in terms of a model. This is the area model, correct? And we're trying to express 3 times 5. So that means we have 3 rows of 5, and that gives us 15. Now if we commute, we want to discuss 5 times 3. This would be 5 rows of 3 units. And that also gives us a result of 15, and that shows visually the commutative property of multiplication. Now what about the associative property? So how do we associate these values together? If we're trying to multiply 3 times 5 times 4, notice here, the first thing we do is get our pen working. That we've got 5 times 4. What does that mean? We have 5 rows of 4 units. If you look, that's what we have going on here. So we have, and they've then turned sideways, so really the 4 goes this way and the 5 goes this way. Okay, so notice that we've got 5 units, 5 units, 5. I'm looking at the wrong. We've got 4 units, 4 units, 4 units, 4 units, and then the row is considered this way. There's your 5. Okay. And then we've got 3 of those stacked up for you. Now, that answer, if you counted all those, is going to give you 60. Okay? Now, there's a different way we could do it. Here, notice that we are associating the 3 and the 5 together. So that means 3 rows of 5 units. And at the end, there's 4, so we need 1, 2, 3 of the 4 of those depicted. If you count your blocks, that is also 60. So we could say that 3 times 5 times 4 is equal to 3 times 5 times 4, where the first time we group together the 5 and the 4, and the next time the 3 and the 5. It's the same number of blocks every way we do it. So that depicts that we have an associative property. Now, for some reason, this property was not listed before, And the next one I'm going to talk about, I would do well to list it, but we're going to talk about it officially now. And that's the distributive property of multiplication over addition. Okay, let's look at a picture of this. So, first of all, what is the distributive property? Well, it says that, let's write it above, if we have 5, so again, let's get the pen working, 5 times 3 plus 4, then we can distribute multiplication across addition. In other words, we can say 5 times 3 plus 5 times 4. And we're trying to depict that in an image here with our area blocks again. So, first of all, 3 plus 4. So, 3 plus 4, right here, let's just look at the bottom row highlighted. This is 3 plus 4 more. Now, we're multiplying that by 5, and that's why we need 5 rows of that. So there's 5 rows of 3 plus 4. Now, on the other side, this is after we distribute with multiplication over addition. So we're representing our 5 times 3 right here. So again, that's 5 rows of 3 units. Plus our 5 times 4, which is 5 rows of 4 units. And if we smash those back together, you clearly see we have what's over here on the left. So the area of the large rectangle equals the sum of the areas of the two smaller rectangles. So there's your distributive property. And officially, here's the distributive property. A times B plus C is equal to A times B plus A times C. We also have a distributive property of multiplication over subtraction for whole numbers. And so once again, I'm allowed to multiply A times B, and you get AB. You keep your operation minus, and then A times C is AC. So we have a distributive property over addition and a distributive property over subtraction. And then 2 more notes about the distributive property. Look what we're doing here. We have B plus C times A. Now, this is different than what was written before. If I bear with me while I flip back to our original distributive property, that's A in front times B plus C. Is it okay to have the A in the back? Well, they go on to say because we have the commutative property, it's perfectly allowable to distribute from the back. So we're saying B times A and C times A. And you could even distribute, you could use the commutative property beforehand too and put the A in the front and then B plus C, and that will give you AB plus AC. Is that the same thing as BA plus CA? Well, yes, because we have a commutative property of multiplication as well. And so that's the way they were thinking about this. Okay? And also, look at the bottom. We don't necessarily have to just have 2 terms either. This time we're distributing over 3 terms. So the A would get multiplied by each term here. So A times B first, and then A times C, and then A times D. So you can do that for any finite number of terms. You could do A times 50 different terms if you needed to. Now check this out. When the distributive property is written as AB plus AC equals A times B plus C. Now again, did you notice we're going backwards? So AB plus AC, the A is coming out times B plus C. That's called factoring. As a matter of fact, it's called factoring the greatest common factor. You've seen that before. So sometimes you have to use the distributive property backwards. The factors of AB plus AC are A, okay? So A is one of your factors, and then B plus C is your other factor. Because remember what factors are? Those are values multiplied together to get a product. So if I multiplied 2 times 3 times 8 to get 48, then 2, 3, and 8 are all separate factors of 48. This is fun. They want us to use an area model to show that x plus y times z plus w is xz plus xw plus yz plus yw. Now, but before I jump into this model, I want you to notice something and recall how you do this. We often call this the FOIL method in an algebra class. That represents first, outer, inner, last. So you multiply the first together, x times z is xz. Then the last, x times w is xw. Then the innermost, y times z is yz. And then the last, y times w is yw. And that's not what I was trying to show you here. I wanted to remind you where these four terms came from. But visually, we can do this with an area model, and let me show you, okay? So we're multiplying x plus y. Now, I could depict on my model down here that this length is x, okay? So this length right here, and this length is y. So that whole line, you see, is x plus y. Across the top, I can note that this length is z, the short, well, right here, this part, and this length is w, so that whole line is z plus w. Now, to find area, I need to multiply x plus y times z plus w. Now, let's look at the inside. So this rectangle right here, if I just calculate that area, you see that's x times z. Okay, now let's look at another rectangle. How about this rectangle over here? Now that's going to be x times w. Let's look at the rectangle at the bottom left. So this rectangle right here. Now, how wide is it? It's z wide. How tall is it? Y tall. So that's y times z. And then you help me out with the last rectangle. Okay, so we're talking about far corner over here. How tall is that? It's y. How wide is that? It's w. So that's going to be yw. And just in case you miss it, I have it typed up. So again, here we have x and y, and that whole length is xy. Across the top, we have z and w, and that whole length is zw. So to find the area of the entire rectangle, the outside, it would be x plus y times z plus w. But then we could break it down and look at all four rectangles separately. And inside here, we have xz, yz, xw, yw. You add all the four separate areas together to get your expression. Pretty neat, huh? Now, I did this before we did the rectangle thing, but I want to show you this one more time. So we want to use the distributive property of multiplication over addition to show that this is true. Okay? Now, I did it a little bit different this time. Okay, so notice this. If we take x plus y, the entire x plus y, and distribute that inside, it's going to be x plus y times z. That's what we have listed first. And then the entire x plus y times w. That's using the distributive property one time. Now, to simplify this, I bet you can imagine, we're going to distribute the z inside here and the w inside there. We've already talked about you can distribute backwards like that because the commutative property of multiplication. And here we go. Well, we use the distributive property first. I wanted to point that out. So now we're going to use the commutative property of multiplication. Well, we use the distributive property. My bad. We're not the commutative property yet. We use the distributive property. I said that when I did it a minute ago, and then I didn't repeat myself properly. So again, just to remind you, we multiplied z times x. Let's get this pen working correctly. So z times x, z times y, and then x times w, and y times w. Now, is that our answer? Well, not exactly, right? Because these are in a different order. Can I just rearrange that order? And if I can, what property am I using? Am I allowed to do that? Notice I reversed it. It's not reversed there. There it's reversed. Okay, so we use the commutative property of addition to reverse those, right? Whenever you want to change the order of addition, you totally can. It is the commutative property of addition. The next thing I want to talk about is properties of exponents. You have seen this in an algebra class. If a, the base, and n, the exponent, are whole numbers, and n is not equal to 0, so your exponent is not equal to 0. By the way, we have talked about if your exponent is 0, your answer is 1. But this definition is for when n is not equal to 0. Then a to the n is equal to a times a times a times a n number of times. Okay, and you do need to know that a to the first is a. Now that gives us a few properties. One of them is that a to the m times a to the n is a to the m plus n. So when you're multiplying bases, you actually add exponents. Now an example where you could see that done, if I said 2 to the third times 2 to the fourth, 2 to the third by definition is 3 2s, so 2 times 2 times 2. And 2 to the fourth is 4 2s, 2 times 2 times 2 times 2. And I could use some parentheses around this to make it more clear. Well, how many 2s is that? If you count them, 1, 2, 3, 4, 5, 6, 7. That's 2 to the 7th. Notice when you use that rule, you don't do anything with the base. You have to have a common base to use the rule. So they both have 2s as the base. And you actually add these exponents together to get the 7th power. Okay, ready for the next rule? So notice it says when you have a power to a power. So a to the m exponent raised to another exponent on the outside. Notice what we do, we just multiply those two exponents together, m times n. Now if you see this as an example, I think you're going to be able to hang with me. 2 to the third, let's raise that to the 4th power. Now what does that 4 on the outside mean? Well, that means it's 2 to the third times 2 to the third times 2 to the third times 2 to the third, right? There's 4 of those. Now we just learned a rule that says when you multiply the bases, the one right above, you add those exponents. So 3 plus 3 plus 3 plus 3 is 12. So this is 2 to the 12th. Now instead of writing out 2 to the third 4 times, you could just multiply those two exponents together and you get 2 to the 12th power. And the properties of exponents don't end. Here's another one. For any whole number a and natural numbers m and n, if these both have the same exponent, notice they are both n's, then you could write that together as ab times the single exponent. So for instance, if you have 3 to the 4th times 5 to the 4th, you are allowed to write that as 15 to the 4th power. But these exponents now, this is important, these must match to be able to pull that off. All right, what about division? If you divide the same bases, you subtract the exponents. Okay. Now, if you have, say for instance, 3 to the 7th power divided by 3 to the 2nd power, struggling to write a 3, that's going to be 3 to the 7 minus 2, which is 3 to the 5th power. I have a couple of exponent examples for you. So write each of the following with only one exponent. So they want us to write all this with a single exponent. I'm going to do this by hand and then I'm going to show you the typed version. Now here's what I notice. the value 8 could also be written with a base of 2. Why would we want to do that? Well, we need to find a common way to write these, and they're all different. So we have a rule that says when you multiply the bases, you can add the exponents, but they would all have to be the same base down here, and they're not. So base 2 may be the way to go, because I can write 8 with a base of 2, and I can write 16 with a base of 2. How do I do that? Well, 2 to the 6, let's keep that, okay? But now 8, what is 8? 2 to some power. Well, we know 2 to the first power. Let's do some scratch work at the top of the page. 2 to the first power is 2. 2 to the second power is 2 times 2 is 4. 2 to the third power is 2 times 2 times 2. Hey, that's 8. 2 to the fourth power is 2 times 2 times 2 times 2 is 16. 2 to the fifth power is one more 2, that's 32. You could list several of these. I want to keep going because I don't need to. But 8, I'm going to replace that with 2 to the third. What am I going to do with that 5 on the outside? I'm just going to rewrite it up here. It's still there. It hasn't gone anywhere. Look, 16. I can rewrite that as 2 to the fourth power. Now what am I going to do with that 3? It's still out there. So I replaced 8 with 2 to the third. I replaced 16 with 2 to the fourth. Now the next thing I want to do is handle this exponent raised to an exponent situation. Remember what the rule is for that? They're supposed to multiply those, yes. So this is 2 to the 6th times 2 to the 15th times 2 to the 12th power. So 3 times 5 is 15. 4 times 3 is 12. Now I'm multiplying bases, and the rule there is we add exponents. So this is 2 to the 6 plus 15 plus 12, which is going to be 2 to the 21 plus 12. How about 33 power, which is a huge number, by the way. We're just going to keep it as 2 to the 33. When you get a minute, type that in your calculator and see how big that thing is. Now again, I've got this typed up. I think you might find that the handwritten version that we just did is a little easier to comprehend, but here it is typed up. So notice how we replaced 8 right here with 2 to the third, and we also replaced 16 right here with 2 to the fourth. Then we used our properties of exponents to multiply the 3 times 5 to get 15, multiply the 4 times 3 to get 12, and then finally we add 6 plus 15 plus 12. Now you keep the common base. You don't say 2 times 2 times 2. You are handling that when you add those exponents together. You don't multiply the base because they will all match, and you have to keep that matching base. Okay, folks, I have one more handwritten problem and I want to squeeze in before we wrap up this video. But keep in mind, there's going to be a part 2 to this video. So here we go. 6 to the 7th times 2 to the 4th times 3 to the 4th. So now, these have to be a common base for me to multiply them together. But you remember we have a property that if these exponents match, then I could write this as 6 to the 7th. I'm leaving alone. But this can be 2 times 3 to the 4th power. Now we know 2 times 3 is 6, right? So this is 6 to the 7th times 6 to the 4th. And now I have a common base. So I can say that, y'all, it's not 6 times 6 is 36. You keep that 6 base, and we add those exponents together. So 6 to the 11th power is your final answer there. Hope that makes sense. I'm going to shut part 1 down and come back for part 2.